Hey, recording is rolling. It is Thursday, November 30th. I got a bunch of fun rotational stuff lined up. Before I get too deep into that, let me flip my screen over here. All right, and got a fun news story for you guys, or maybe fun, hopefully fun. All right, we're gonna find out. Um, we're gonna have possibly a geomagnetic storm from the sun, like a solar flare, head towards us tonight. Uh, so let me tell you guys a little history story. You guys know something from 1859 called the Carrington event? Carrington event. Who knows about the Carrington event? No. All right. So a little bit of history here. So the sun is on a 11-year solar cycle of intensity. So every 11 years goes through the cycle, it gets like more and less intense. Guys, everybody look up here. Everything about this? Right. And then uh, right now we're at a maximum intensity point. Uh, 11 years ago, we're at a maximum. If you go back like 15 cycles ago to 1859, there's this event where there was a solar flare that was so strong that hit the Earth that you could actually see the northern lights all the way down here in Florida and even further south, like Cuba. You guys know the northern lights, right? Those northern lights, aurora borealis, that you normally have to go like way up north to like Alaska to see. Right? You can see it all the way down here in Florida. Right? Now the storm was so big. Let's see, what technology were they using at the time? Telegraphs. Telegraphs was like the frontline technology. People who were operating telegraphs were getting electric shocks. There's this whole conversation between these two people that realized that they didn't even have to have the power system turned on to operate this thing. They said, well, we got the batteries turned off, or we're still like messaging each other, right? Because the power source was the sun, right? Just the solar flare was just powering everything. That was 1859. Now nowadays, the whole world is hooked up and run by like all these computer systems. So if some kind of this Carrington level event hit the Earth nowadays, what would that be like? Who knows? Who's to say? I have a feeling we might not quite be as prepared for this as might be expecting. Um, there was back in 2012, there was one of these type solar flares that almost hit the Earth. It just barely missed us back in 2012. But guess what's headed towards us right now? Yeah, one of these big old solar flares. It's supposed to hit the Earth tonight. So look up in the sky tonight. You might possibly be able to see the northern lights. I don't know. I'm going to be walking around tonight, and maybe nothing, but maybe we'll be able to see the northern lights. That'd be pretty cool if you could. So yeah, look for that. All right, let's flip back over here. Go to main stuff today. Okay, so a bunch of guys before I hit record just picked up your CMA quiz from your folders. That was the energy and momentum quiz you guys took the day before Thanksgiving, right? So you guys got those back. If you want to do corrections, you can do corrections, just like normal for quizzes. So I circled all the right answers like I always do. Just write out an explanation for why the right answer is right, or if it's an equation, write out the equation, right? Right. So back a few days ago, we started this rotational dynamics, and I was going through all these posters, and I really could have used like 5 or 10 more minutes of class back on Monday. So we're gonna do the last posters today. I got some demos lined up for you guys. Got gyroscope, right? And then the last about 15, 20 minutes, near the end of class, we'll solve as many textbook puzzles as we can solve, right? So that is the plan. All right, let's do some posters. I'm gonna pick up about well, I think you guys didn't see this one, but it's good segue back onto like the rest of this story here. Okay. So the last few days we've been talking about torque, right? You guys just did like a 2-day torque lab, right? You guys did the seesaw lab. You guys did the scaffolding lab. That was like this line right here. So we've been focusing on torque R cross F, right, for quite a bit, right? But let's go into the line right below this, angular momentum. Now, angular momentum is analogous to linear momentum, right? You guys remember linear momentum was mass times velocity. This was a vector, direction mattered, that's it's vector, right? This was conserved in closed systems, right? Same story with angular momentum, except it's rotating. That's it. It's rotational inertia times angular velocity, right? So also a vector, also conserved within closed systems. So what does that mean? Right? Here we go. Angular momentum is I times omega. Right? It's sum of angular momentum before equals sum of angular momentum after in a closed system. Right? My classic example is a figure skater. If you're say like have your arms spread out, that's a large rotational inertia, right? And you're rotating at some rate. So there's omega. Right? Then you bring your arms in, which takes some work to do. So it takes some work to bring your arms in, right? It's force times distance, right? Probably add some kinetic energy to the system, right? Well, this property right here is conserved. So the fact that you shrink your I value means the omega has to increase, and then you increase your spin rate. Right? I think, did you guys see the Paul Hewitt demo of this? Right, Paul Hewitt stood on a turntable, he had the weights out, pulled them in, right? Easier to rotate, gang, harder to rotate, easier to rotate. Right, you hear that, right? All right, so there you go. That one's fun. That might show up at some point. Right. Now, what is the connection between this and torque that you guys have been looking at the last couple of days? Because there is a connection, right? So let's do this right here, right? I think you guys may have seen this one too, right? But let's go back go over what's this talking about. Say I have a turntable, right? You guys remember those turntables from a few weeks back, right? You wind a string around it. So you got strings and pull on a string. And if I apply with a constant force at a constant radial distance, that's a constant torque, right? R cross F gives a torque, which is going to cause us to speed up spinning, right? And speed up spinning in physics, that's called angular acceleration, right? Now, how much angular acceleration? Well, it depends on like, well, how massive is this disk, right? How is the mass distributed? Well, that's called rotational inertia. So here's one perspective for torque, R cross F. That's like the supplied torque. That's also equal to I times alpha. So you can set those equal, and you can solve for like angular acceleration. Right? Now, how do you solve for I? What's the rotational inertia of a disk? Right? Remind you guys how to get that. Right? So a disk is a solid cylinder, so it's just this turned sideways. Like if I turn this way, there's your disk, right? So this has been worked out to be 1/2 mr squared. So if you know the mass of the disk and the radial size, you do 1/2 mr squared. You get I. Boom, that's that I. There you go. Or sometimes in textbook puzzle that might be given to you, right? Now, it said there's a connection between torque and angular momentum. That's this pink box right here. That's like the figure skater, right? So angular momentum is I times omega. Now, omega, you guys remember, is angular velocity. So at some particular time, it's rotating so fast, right? And if you're applying a torque to cause an angular acceleration, then omega is always changing, right? Back to like kinematic type value, right? If you're accelerating, your velocity is changing, right? So if you have a constant torque, I bet the angular velocity is increasing at a constant rate, and therefore L is increasing at a constant rate. And I have a couple of graphs to tell that story that I just told. So everything I just said verbally, here it is couched in 2 graphs, right? So torque versus time, angular momentum versus time. So if you apply a constant torque, hey, there's a constant torque. Turns out that torque times time is equal to the change in angular momentum, like the acquired angular momentum, which on this graph would be the area of that rectangle, right? Now, angular momentum versus time, here it is increasing at a constant rate. Turns out that the rate change of angular momentum is torque, right? So the area under this graph is equal to the coordinate of this graph. The slope of this graph is equal to the coordinate of that graph. There you go. Right. So that's a little bit more involved, a little bit more abstract, but there's that. Right. Right. I have another kind of abstract idea for you guys, but I just want to throw this at you. So like, this exists in the universe. Here's kind of how this works. Is what if you have like the swivel stick? See how this can rotate about this point? I especially have to make this poster because my AP kids definitely need this one because AP always asks the question, right? Right. And you like throw like a point mass at it, and it has a collision right here. Bam! Right. Now maybe it sticks inelastically, maybe it bounces off a Boeing elastically. I mean, there's different variations of this question, but the question is usually like, how fast does the swivel stick get rotating? That's like angular velocity omega. How fast? Right. And how would you even begin to approach that? And the way you do is right here. You say, well, this point mass had some an associated angular momentum. Now, that's a weird idea, right? It definitely has linear momentum, mass times velocity. But if you further take that linear momentum and multiply by this radial size, that's an associated angular momentum. And what can you do with that? You can take that L, and you can set that equal to I times omega of the stick. And you can figure out what is omega for the stick. You guys remember I for a stick rotating about its end happens to be 1/3 ml squared. That comes off this table, so that could possibly be useful too. Right? All right, so you go, like for this class, I think that's probably as deep as we're going to go. That exists. That's kind of how you approach that. Right? Spinning a basketball. Ooh, this one's fun. Right? So you have a basketball in your finger. You put a force at the edge. Give it a spin. Right? How fast does it spin? Or how would you even solve that? Here's exactly how you solve it. Okay? So by applying a force at some radial size, hey, that's a torque. That's R cross F. Okay, so you're applying a torque, right? And if you apply that torque for some time interval, which might be a tiny time, maybe it's like a tenth of a second, bam, right? That's going to get the ball in motion. Torque times time interval. Oh, where have I seen that? I just saw that like 2 minutes ago. That was, hey, that's this green rectangle right here. That's torque times time interval. That's the area of that rectangle. That's the change in angular momentum, right? So you gave it some angular momentum. What is angular momentum? That's I times omega, right? So, okay, so there's torque, it's R cross F. There's the time interval you apply that for, like bam, maybe like a tenth of a second. That's I omega. Okay. Now, here's where it matters what shape that we're trying to rotate. The fact that it's a basketball, that's like a spherical shell, isn't it? Like a spherical shell, right? So I need to know how much inertia are we even talking about, right? So I pull up this table, I say for basketball, it's 2/3 mr squared, bam, make that substitution right there, right? Now, the whole question is, what is omega? Like, how fast is it rotating? Angular velocity. So do some algebra, switch some stuff around. This ends up being the answer for a basketball. Okay. Now, what if you swapped out the basketball for any other shape? What if it was like a solid foam sphere, right? You have like a solid ball and pow, you try to spin that. I bet that's going to rotate differently. Like how differently, right? Well, what would change about this? See, I bet that F would still be locked in place there. The time interval of knocking it would still be there. The mass of the ball would still be locked in place there. The radius of the ball would still be locked in place there. What would change would be this 3/2. This 3/2 only applies to basketball. I can tell you if it's a solid sphere. We can do some really fast math right here. Here's a solid sphere. Got 2/5 instead of a 2/3. So it's 2/5, and this would come out to 5/2. That's exactly what it would be for like a solid foam ball. All right. Now let's do a ball rolling downhill. We're getting near the end here. We just got a. Oh, I want to show you the other one first. All right. Just got 3 posters left. Getting close to the end. Right, so if there's a ball rolling downhill, the classic question in a physics textbook is usually, what's the linear speed of the ball at the bottom, right? And so how would you solve that, right? I have 2 different posters for how to solve that. They both lead to the same answer, but one's the hard way, one's the easy way. You guys are looking at the hard way right here. So I want to show you guys 2 different ways. But you guys have seen the physics all over the place. A lot of times there's multiple ways to solve problems, and if physics is all self-consistent, it always should lead to the same answer, right? It all works. Here's the hard way to do it. You can do it through torque, right? Now, torque, you need 2 different forces at some radial distance of separation, right? And that's what you get here. So one force is the weight of the ball itself. That's mg, right? Now, the normal force doesn't actually cause a torque, so you can kind of ignore that one, right? But the fact that there's a friction force is important. If there was no friction, the ball actually would not rotate. It would slide down without spinning, which would look weird, right? So we're going to have a friction force. Ideally, it's a static friction force, so there's no sliding. A lot of times the textbook will specify rolls without slipping for that reason. Right. So it's going to induce a force which will induce rolling, right? So we've got torque equals, now it comes out to this. Here's your R cross F. Here's your R. Here's your F. Sine theta, right? Like a cross product, right? I would explain that a little bit more, but maybe I'll just leave that for you to think kind of deeply about that. If you're really curious about that, think why it would turn out to be like that, right? Now torque is also equal to I times alpha. Here's where I'm going to substitute in I for the basketball. Ooh, but you need one more detail here. Almost forgot to mention, right? The fact that the basketball doesn't actually rotate about its center. It's actually rolling about this pivot point right here, okay? Rolling about that pivot point. Means you have to take its regular rotational inertia about center and shift that along this parallel axis. So it's rolling around the bottom, and it changes to look like that, right? So that's that substitution right there, right? Then you can solve for the speed at the bottom, and you get this expression right here. Okay, boom, boom, boom. There you go. Right. Now that's a really long, kind of difficult process, right? But there is an easier way to solve that problem, and that's using energy conservation. Now, energy conservation. Let's go back to our starting checklist. Right, is the very last row. Energy is like the very last row of this table. Right? You guys remember kinetic energy linear was 1/2 mv squared, right? Well, what's the rotational equivalent? 1/2 I omega squared, right? Instead of m, it's I. Instead of v, it's omega. Right? And so how are we going to use that to figure this out? The ball rolls down an incline using energy. Because what kind of energy at the very top? Potential energy. There's your MGH, right? So energy is conserved, closed system, MGH at the top, right? What kind of energy at the bottom? Kinetic, right? It turns out 2 different kinds of kinetic. If you point a radar gun at it, you're getting a linear speed. That's the question, by the way, is what is that linear speed? That has something to do with this 1/2 mv squared. But don't forget also that the fact that the ball is rolling, there's some energy that goes into making it rotate. That's your 1/2 I omega squared. Now, from using this method, it's okay to think about the ball rotating with respect to its center, right? It's different from the torque setup, right? Okay, so we got this setup. All right. Now, some of these variables are related to each other. Like this I is related to this M. I know for a basketball, it's 2/3 mr squared. So that's that substitution right there. And I know this omega is related to this V. Omega is like V over R. You might remember that. Oh, actually, I got that with them reaching distance 2. That's like this right here. There's a connection, right, between V and omega. Right. So give you the substitution right there. Bam. Right. And then a little bit of algebra later, I get the exact same answer that I got using the torque method. Like I said, right? So if you know the fact that it's a basketball has something to do with the 6/5 gravity of a planet, the height change of the hill, right? Notice that the sorry, one more thing. This H, you might have to do the step here. You guys see it said H is L sine theta. Isn't it true? H is L sine theta, right? That might, depending on what you're given in the textbook, right? That you might have to do that substitution, right? Notice that the mass and the radial size of the ball end up canceling out. So if you had like a small basketball and a large basketball side by side, different radial sizes, different masses, ideally, according to physics, they would actually tie. Like they would, if they were like in a roll race, right? They would both reach the bottom of the incline at the same time, and they'd have the same linear speed at the bottom, right? Because the mass and the radial size end up canceling out, right? What does affect the rotation of the ball is the fact that all the mass is distributed on the surface for the basketball. So, all right, that brings us to the very last poster for this section, right? Suppose I have a bunch of rolling objects, right? Now they will roll down differently because the mass is distributed differently for each one. Let's ignore the air hockey puck for a moment, right? These 4 guys are rolling, not the air hockey puck, but these 4 guys are rolling. Right? So the bowling ball has its mass distributed closest to its center for comparing all these 4 objects. So it's going to win the race. It has the least amount of energy that goes into making it rotate, right? Followed by the cylinder, followed by the basketball, followed by the ring. Now the ring has its mass distributed furthest out from the end, compared to these 4. So it's always going to lose this race, right? It's always rolling the slowest. Okay, there's that. Right? Again, the mass, the exact mass and radial size end up being unimportant, but the distribution of the mass is what matters. Okay? Right. Now let's bring in the air hockey puck with one frictionless lane. Notice that there's some static friction with the rolling objects. You need the static friction to make it roll, right? There's only one lane I have here that's actually frictionless. So here's my air hockey puck. You guys notice that's going to beat all these other guys, right? It's because none of the energy goes into making it roll. All of its energy goes into translational kinetic. Okay. Do you guys remember how fast does the air hockey puck move at the bottom of the incline? Square root 2gh. You guys remember that? Square root 2gh? Right? Which you guys have seen like at least a dozen times in this class. Okay? Right. Let's compare that to this basketball. Ooh, square root 6/5 gh. 6/5, that's like 1.2. Hey, that's like not as fast, which makes sense, right? It's slower, but it's not crazy slower, but it's a little bit slower than the frictionless air hockey puck. There you go. All right. So that's the last poster. You guys got any questions about those posters right there? All right. Let's gonna do some demos with you guys. Let's do here, guys. Well, I should have one kind of stuff in front of me. You guys ever play with a gyroscope? A gyroscope? No, or some yes, some no. Okay. I bet you guys have played with some version of a gyroscope. Have you ever played with a top, like spin a top? Yeah. Okay. Yeah, that's like a version of a gyroscope. If you ever spin a top. Also, I have these Roosevelt set up. Right. Can you set a coin on its edge and it bounces on its edge? Okay. It's really hard to do. Right. Maybe you can do that with a nickel. But these Roosevelts, it's really hard to balance it on the edge, right? It's really hard to do that. Guys, how can I stand the coin up on its edge so it actually stays up on its edge? Give it a spin, right? Because now it has angular momentum, which wants to be conserved. So it doesn't want to change its orientation and it stays upright. That's a version of a gyroscope too, right? I got one kind of stuff here. I'm going to pull a string and see if I can get this to work. This may or may not, but we're going to find out. We're going to find out, right? See, like if I hold this up, it falls over, right? But just like if you spin a top, it should stay upright. String broke. Let's try this again. I think it's been fast enough. All right. But rewound itself. Let's try one more time. Aha! Look at it go. Oh yeah. Oh yeah. Stand right. Right. So because again, it has angular momentum, it doesn't want to change its orientation. Now you might think, well, it's probably like starting to tilt and fall over. Why doesn't it just like fall straight down? Like there is like a torque, but there's a weight, like a force, and also a torque, right? And then just fall over. Right? But when it's spinning, what makes it like stay straight up, right? So here's where it's good. Video time. Switch my screen back over here. Got a couple of videos queued up. Right, one is just on gyroscopes itself. Now this one I've got muted. I'm just going to narrate this myself. You just, oh hey, look, it's the same type gyroscope. Right? He talks about how a gyroscope works. He says like if it's not spinning, it just feels like a regular object, falls over. All right, but give it a spin, and you'll notice right away it feels different. Like if you try to change its orientation, you'll feel a resistive force. It's hard to change its orientation, right? I also have a bicycle wheel version of this. I think I'm going to cart out tomorrow, probably. Like, tomorrow's Friday. And you guys can feel this too. So if you have like a big old bicycle wheel and you give it a spin, you'll notice that it's hard to change its orientation. You'll feel a resistive force. It doesn't want to change its orientation. Okay, so there you go. It stands straight up. How about this? What if he puts it like on an angle? What's it going to do? Ooh. It looks like it's levitating, right? Which is weird. Like if that was encapsulated in like some paper box, it'd be hard to know. Like why is it like levitating like that? Why does it fall over? Right? Also notice that it's processing around, right? Which is something you'll see too. That one's pretty vertical right there, but if it has any kind of angle to it, it'll like process around. Right. Oh, we're about to see another procession right here. Let's watch this. Right. And what causes like that processing, the processing type motion, right? Okay, near the end of this, he talks about some technology applications. One technology application is you can put this in planes. Right? Let's suppose it's a really dark and stormy night and you're in a plane. It might be really hard to tell the orientation of the plane. There's even been cases where pilots have been flying upside down and not even known that because just how like physics and dynamics, right? So a gyroscope though wants to maintain its orientation. So if you have a gyroscope inside there, then as the plane's tilting around, the pilot doesn't really know what's going on. The gyroscope can send signals to the plane and tell the pilot, oh, you're actually like tilted like so many degrees like that. All right. But really, I think the best explanation that I've ever found is this right here, channel of Vsauce. You guys know this channel of Vsauce, right? I think it may have played some stuff for you guys. All right. Anyway, I'm going to post this link to Google Classroom, and I really do recommend that you guys watch this. This is a really good video. It's called Spinning. So I'll post this link to Google Classroom. It's like 17 minutes long. I'd really like to share in class, except we're always like short on time, right? But I will give you guys a quick encapsulation of what he talks about. So he breaks out a gyroscope too. I think it's like the same type gyroscope. And so the title of the video is Spinning, right? He talks about rotation. He goes back and look, he gives you guys a nice review of centripetal force. Now we did that a few weeks ago. You guys remember centripetal force? He talks about that. This all leads up to this gyroscope, right? He talks about angular momentum, right? Okay, right here is a good explanation for why even though the gyroscope is tilted over, it doesn't actually fall a particular direction. It says, what if you take that gyroscope, which could be like this green ring right here, and you split it into like 1 billion points, and you just focus on one point, which, hey, could be like a satellite orbiting the Earth, right? So now we got a satellite orbiting the Earth. Notice that it has an eastward momentum. You guys see an eastward momentum? Okay. What if at this point you knocked it straight south, like you put straight downward force, like bam? What would that satellite do? Well, it would move down in response to the force, but it's still moving eastward because it was moving eastward initially. It has an eastward momentum. So it doesn't move straight south. It moves kind of southeast is what it's going to do, right? It's ultimately going to set up this new orbit that's this blue ring, right? So see if you guys are following. By applying a downward force at this point that is shown right there, it doesn't change its orbit straight north-south. It still continues to move east at that point, and its new orbit actually sets up along this blue orbit, right? So now let's replace the satellite with like back to 1 billion satellites. Hey, let's get a solid ring. Oh, now we're back to the gyroscope. So now if the gyroscope was that green ring, and it's like starting to tilt over, let's say towards us, which would be like a downward force, like its own weight's trying to pull it straight down. it doesn't topple over in that direction. Instead, it sort of topples over 90 degrees ahead in its motion. And that's what causes that precession moment, right? That precession motion, right? It's also, well, this video goes on a bit. He does the bike tire, which again, I think I want to do tomorrow with the ice, right? So I will post that link to Google Classroom. I do highly recommend you watch that. It's like 17 minutes. So there you go. Vsauce. All right. All right, so back over here. I think we're ready for textbook puzzles. Are you guys ready to solve some textbook puzzles? We'll do as many as we can today, and then we'll save some more for the future. Textbook puzzles.